Hello everybody, it's Mr. Steele. I'm going to be working through problems from the Calculus BC ESQ model. It's brand new, as in it's October 9th at 6 p.m. and I wrote this out at I think about 8:30 a.m. this morning. So I'm just going to work through as many problems as I can in each sitting or standing, and I'll try to compile this over the course of the week. So we'll see how far I get in this case. I don't think I can get that far. I think there were 45 separate problems that are appearing on here. So basically it's going to take me a little bit of time. Question number one is focused on graphing functions. In a sense, you're meant to sketch the graph, so it doesn't need to be the most precise graph ever, but it does need to be accurate. And if you hear precise and accurate as different words, they are, in fact, different words. I'm using them that way. Precise, I mean like every point is exactly where you want it to be, whereas accurate means I want it to be a good, strong representation of the function with the most important points accurate and precise, but the rest can be a little bit less careful. Like we're not going down so far as to make sure you've got the correct concavity in this case, just as a heads up. So in here, in this first case, the first type of function that we're looking at is a polynomial. In fact, this is in sort of the classic Franklin noodle bowl form. So we've got everything sort of separated out into factors. That makes this really convenient. And it tells us some really important stuff, like right off the bat. Not that you have to write this, I'm just doing it for clarity's sake. Right off the bat, I noticed that we have zeros or x-intercepts at 1, -3, and 6. And that's a pretty significant piece of information, particularly because 1, 0 is a double root, so it's going to have a bounce. The last thing that I'll find here, since we are being asked to find intercepts and asymptotes, is that I should also note what the y-intercept is. And to find that y-intercept, just plug in 0. So again, while I do this in my head, and I imagine many of you do as well, just for the sake of visualization here, we got 1, 3, -6. It looks like we're going to get -18. So I'll look and see if that works out that way. So according to this, we're going to have zeros at -3. Going to have a 0 at 1. That will be a bounce, but I'll hit that in a second. And then we'll have 1 at 6. And then our y-intercept is -18. I will label it afterwards. Like I said, accurate, not precise in this case. As far as other things, in Franklin terms, we would call this a positive noodle. I had positive noodles for dinner last night. In this case, we're calling it a positive noodle. That is to say that it has a positive leading coefficient, so a is greater than 0. Don't write it that way. I'd rather say it that way. A is greater than 0. And likewise, we would say that our degree in this case is going to be 4. So it's not a noodle at all. Liar. I'm a liar. It's a positive bowl. Was I positive about the noodle? I was not. Be careful what you say. Based on this, positive bowls behave, at least in the end behavior, like positive parabolas. So we're going to start over here. Going to go back down through. We'll bounce off at 1. Then we'll continue back upward. So there is our positive bowl. This would be the graph of our function y. I want to label the intercepts. So that's -3. That's +1. And that's going to be +6. I don't know why I put the plus sign there. It was not necessary. And then last but not least, we said there was a y-intercept of -18, so I'll label the -18. Nothing else needs to be labeled here. Like, do we have paths to find the maxima and the relative maximum we have? The two minima, we'd have to use calculus and some pretty intense factoring and like maybe even some fancier techniques than that. So that's more than enough. We're looking for, as it says up here, intercepts and asymptotes. There are no asymptotes on a polynomial. Turned out 4 intercepts, and we labeled all of them. The next one we're going to look at is y equals 3 to the x plus 2. I was reasoning out this morning like what my expectations were, or what your expectations should be for how much stuff you might need to label on a graph. And I think my goal is always to have you label between 2 and 3 things. I know the polynomial in the previous problem involved multiple things, but I'd say polynomials, since they're factored that way, it's fair to ask you to plot multiple intercepts or more intercepts than normal. In this case, for an exponential function, it's worth pointing out that they have a couple different defining traits. Of course, they could have x or y intercepts, but the most important thing for us to note in an exponential function is the horizontal asymptote, and that occurs when y is equal, or at y equals the constant, and our constant in this case is 2. If you want to think about that in terms of calculus terms, that's like saying the limit as x goes to -infinity of 3 to the x plus 2 is 2, which is an accurate value, by the way. So what that means is in our graph, we will have a horizontal asymptote at y equals 2. And although there are times where I'm pretty forgiving, in this case I do want to see y equals 2. I want to see that label right there. And again, we don't have to be precise, we need to be accurate. So labeling it as y equals 2 eliminates that ambiguity. Next, as far as our shape, an exponential is flat on one side and then grows really steeply on the other. So in our case, like we can sort of see what's going to happen here. I would expect it to look like this. In fact, that's probably a perfect graph, so I'm going to leave it. But we should make sure that we check things like the x and y intercepts first. I'll start with the y-intercept in this case. The y-intercept will happen when x is equal to 0. So in our case, if we plug in 0, we get y equals 3 to the 0 plus 2, which is not 2, even though your brain's telling you that. This is 1 plus 2 equals 3. So we're going to have a y-intercept at 0, 3. I'm going to go ahead and label that right here as 3. Now, if you're wondering where the x-intercept would be, just to kind of verify why this isn't going to happen, to get an x-intercept, you set y equal to 0. So it'd be asking when is 3 to the x plus 2 equal to 0. It's like asking when is a power of 3 equal to negative 2. And that's like I want to write nuh-uh, but that's not a thing. There are none. We'll just put none. So x is the empty set. So in fact, there is no x-intercept, which we can see from our graph because our function never crosses down there. The horizontal asymptote lifts it above, so our graph never crosses the x-axis. And that gives us our accurate graph. That's all that it took in this case. If you wanted to add an extra point to give a little bit more shaping, great. That's like more power to you. But for us, this is all we were asked for. Asymptotes, intercepts. Notice there were 2 for a more advanced graph that felt appropriate. Then the last one that we're going to look at here, I think this is the last one in the graphing section, is log base 2 of x plus 8. I included a log graph. I mean, by the way, I think it's pretty obvious that this one's a logarithmic function because of the presence of the word log. That's a valuable piece of information to deal out here. But I wanted to include these because people tend to forget their shapes. Log functions have a vertical asymptote, and then they're just the exponential function, but as an inverse, which means that it gets reflected across the line y equals x. So they'll look just like this, kind of like if you turned your head while looking at an exponential. That's our stuff. So the important things for us to find begin with an asymptote. So our vertical asymptote is going to be wherever the argument, which in our case is x plus 8 equals 0, that's going to give us x equals negative 8. So effectively, you can imagine we're going to have a vertical asymptote over here, and I'll label it as x equals negative 8. For the others, we are going to have both asymptotes in this, or excuse me, both intercepts in this case. Sorry, I'm pretty tired already. To get our x-intercept, we're going to set this entire thing equal to 0. So we need to know when is log base 2 of x plus 8 equal to 0. Now I imagine many of you can see that this is negative 7, and if you can, that's awesome. If you can't, I'll even use a different color. We can exponentiate base 2 on both sides. We'll get 2 to the 0 is 1, and on the right side, 2 to the log base 2 divides out, and that means that 1 is equal to x plus 8, or x is equal to negative 7. So there's going to be our x-intercept. And then finally, to get our y-intercept, I'll go back to the original color. For our y-intercept, we plug in x equals 0. So in that case, we would have log base 2 of 0 plus 8. This is sort of the classic log fact. In fact, it's the one that I kind of use to always keep myself grounded in log world. What power of 2 gives me 8? That's 3, which means that our y-intercept is going to be 0, 3. So I can go over here and label it, but instead what I'm going to do, smart move, math pro tip, I'm going to sketch my graph shape a little bit, try my best, go through my dot, and then through the y-axis, and then afterwards, only afterwards, I'll label this as 3. Now other than adding that arrow down there, like I've got everything covered. Now, as a heads up, there's a really common wrong graph people draw for logs all the time. They draw this. Like, what shape is that? Radical. Yeah, it's not just a radical, it's an even root. You should all be more careful when you respond to my rhetorical questions. But yeah, that's not it. That's not a log. Like, logs continue downward. So for logs, I really should see arrows to indicate that. But if your graph does continue downward, I will assume that it's there as long as it stretches to the bottom of the graph. So just FYI. Question number 2. People tend to feel less comfortable with trig, and to be fair, I guess I didn't feel that great with it in high school. It took me a little while to get comfortable with it. But I think the nice thing is there's only so many questions we can ask you. And on this model, one of the reasons I rewrote it was I wanted to be really explicit about the types of questions I might ask you with a topic like trigonometric equations. Because there are tens of thousands of equations that could be asked here, even involving just special angles and quadrantals, but I tend to ask them in certain forms. The first one that you're seeing right here, question 2a, is the form that lets you prove to me that you can work within multiple trig ratios, that you can solve equations involving sine, solve equations involving tangent, basically a couple specific functions all at once. So in this case, the key element that we use is actually a classic middle school math thing, which is called the zero products property. Since these two things multiply to 0, one or both of them have to be 0. So that's exactly what I'll say, is either root 3 tangent of x plus 1 has to equal 0, or sine of x, or sorry, I'm skipping ahead. I really wanted to skip ahead. They do this first step really fast. Or 2 sine of x minus root 3 equals 0. So from here, tangent of x would be equal to negative 1 over root 3. Over on this side, though, sine of x would be equal to root 3 over 2. So we have two possibilities. And then for each of these, we can visualize a trigonometric unit circle, or a unit circle, not necessarily trigonometric, and just imagine where these fall. So tangent is negative in quadrants 2 and 4. I use always stack the cash. You can do whatever you want. Sine is positive in the first two quadrants. And since we're opposite the root 3, this on the right side is going to be a 60-degree root angle, or a 60-degree reference angle, excuse me. And on this other side, we're going to be opposite the 1s. So effectively, this is going to be a 30-degree reference angle. So given all that, we can get our four answers here. On the left side, since they're all 30s, those are pi's over 6 in the radian unit measure. So effectively, x will be 5 pi over 6 and 11 pi over 6. And then from that other side, we've got what looks like pi over 3. And since we're in quadrant 2, 2 pi over 3. Now, if you're wondering what happened to the other infinity solutions, because technically these things will forever, yeah, there are more solutions, but we were specifically requesting those in 0 to 2 pi. So only need those four. Those are the four we're looking for. The second question we're going to look at is sort of an abbreviated version of the one we used to ask here. In a sense, this is a question that I think I forgot for a long time, sort of what the purpose of asking this was. I was just testing your trig skills. But that's not actually what we use it for here. We use this to set up the limits of integration for polar areas. And to do that, we only need the two smallest positive solutions. So that's what we're focused on here. So in looking at this particular question, there's a couple things thrown at you. First of all, we have 3x in the argument. That's why we're talking about the two smallest positive solutions rather than just solving it. Second, we have cosecant. So we have a reciprocal function. So I'm going to do two different moves here to get us into position. The first thing I'm going to do is I'm going to move the positive 2 to the other side and make it negative 2. And then second, I'm going to take the reciprocal of both sides. And I do that just kind of like by thinking about it. But in case you're not sure what I'm doing in this case, I'm just taking the reciprocal of both sides. On the right side, our equation is going to be equal to negative 1/2. On the left side, 1 over cosecant is sine. So this is really the sine of 3x equals negative 1/2. Now in here, as I picture this, sine is negative down here and down here. So effectively, we're looking at this. Sine is 1, so this is a 30-degree reference angle. And we can see that those angles that we're thinking of here are going to be 7 pi over 6 and 11 pi over 6, which I think we saw in the first problem. But there's a difference here. The difference is this isn't just sine of x, it's the sine of 3x. That means 3x, that argument has to be equal to 7 pi over 6 or 11 pi over 6. Now to get rid of this mess, all we have to do is multiply by 1/3. You could also say divide by 3, but I prefer to just kind of note that we're multiplying. I think that somehow is a little more intuitive. That gives us that x is equal to 7 pi over 18 and 11 pi over 18. And as a heads up, those are our answers. Like that's what we're looking for here. We wanted the two smallest positive solutions, them or that. Those are the smallest positive solutions. Now, having said that, if you were doing a different sort of trig thing and you stumbled upon this thinking, yeah, well, how do I find all the solutions in 0 to 2 pi? To find the other ones, recognize that the solutions are the consecutive solutions that are coterminal to one another. I don't know if coterminal is that the word I'm looking for. It's not the correct word, but we're looking for the other solutions that sort of follow the same pattern, that are following that same symmetry. Symmetry is the word. I'm definitely tired. To find those other ones, we could calculate the period of this function. So for trig functions, except for tangent and cotangent, our period is 2 pi over b, and our b in this case was 3. And if we wanted to go a little bit further to find the others, we could use a common denominator to write this instead as 12 pi over 18. So if we wanted to get more solutions, we could just keep adding 12 pi over 18 to each of these. For instance, this would give us 19 pi over 18. This one would give us 23 pi over 18. And if we kept adding, I think we'd get one more here. 31 pi over 18 and 35? Yeah, 35 pi over 18. Those would be our others. So there are actually 6 solutions on the interval from 0 to 2 pi. But that's not what it asked for. It wanted the two smallest positive solutions. So actually, I'll disagree. It wanted the two smallest positive solutions. So, hey, we're done. There it is. And again, I have a feeling this will be like, I think we're doing 6 ESQs this quarter. I have a feeling this will come up twice. You know, I might do it 3 times. I might do it 3 times. Since there's 2 on here, I think that's appropriate to do it 3 times. Okay. I can feel my energy sort of waning here too. The fact that I'm like saying some things incorrectly too makes me think that I probably should stop early. I have to make a quick grocery store run as well. I went last week, but then I ran out of eggs, so. Okay, the next little section that we have are evaluating each limit. And while I'd like to mimic the original instructions, which said things like use an appropriate algebraic technique, yeah, don't. Like, just get it correct. Like, let's just get it correct, right? Like, that's probably the most important thing here. So, use any appropriate technique. Now, of course, when I say that, you're like, L'Hopital's rule. Yeah, L'Hopital's rule is absolutely the correct tool, and I'm going to use it probably in almost every problem. But you've got to make sure that the problem in question is eligible for L'Hopital's rule before you begin. So in this first limit, which I'm sure you've already 4x plus 11'd in your head, I want to first plug in -5 and make sure this works. So this is 2 times 25 minus 55 plus 5. That's going to be 55 minus 55 is 0. Good stuff. And then down below, pretty obviously, -15 plus 15 is 0. So this combination tells us that we have an indeterminate form. Rich vocabulary, get it all into the video. But this means we are eligible to use L'Hopital's rule. So I'm going to use L'Hopital's rule. So remember, in order to use L'Hopital's rule properly, not that an ESQ reveals this, like gives me a chance to take away these points, but you have to write it as the limit of the ratio of the derivatives. So I need to see the limit when you do L'Hopital's rule. So let's practice this accurately, right? Like, why not just practice accurately while we're here? So there's my first move. So there's where we start. Now I'm going to differentiate the numerator. That's going to very quickly be 4x plus 11. And then I'll differentiate the denominator, which is going to be 3. From here, this is clearly not going to be indeterminate because we don't have a 3, or we don't have a 0 in the denominator now. So we're instead going to have -20 plus 11 over 3. As a reminder, you do not have to simplify your answers here, but I have pride, so I'm going to. Franklin pride? No, just pride in general. Pride like the Lion King. Wait, that didn't end well. The answer is -3. So pretty straightforward problem. You could have absolutely factored and gotten this to work just as well. In fact, I bet I can do that almost automatically. Since the denominator goes to 3 times x plus 5, the numerator is going to be 2x plus 1 times x plus 5. Let's see if I got it again. If I do it this way, that's going to be -10 plus 1 over 3. Look at that. It's exactly the same. Because of course it is. It doesn't matter which structure we choose. Or it doesn't matter which method we use. The structures are the same. So there you go. Whew. Okay, our next one, this is the, like, you probably have to use L'Hopital's rule. I mean, always check first. Of course, always check first. It's worth that 10 seconds because it might just be direct substitution in disguise. But in this case, I'm feeling pretty confident here. That's e to the 0 minus e to the 0. Even if you don't know what e to the 0 is, it's clearly equal to 0. And then down below, we get sine of 0, which is definitely 0. And of course, there's no algebraic technique that we have available to us that will take care of this. So I'm going to go ahead and use L'Hopital's rule. So as far as L'Hopital's rule, I've got to differentiate the top and the bottom. As a heads up, all 3 of these terms that we're going to differentiate use the chain rule. So in other words, we've got to take the derivative of the inside. Down below, I'll start there just for simplicity. We have the sine of 3x. The derivative of sine of 3x is going to be cosine of 3x. But the derivative of the inside is 3, so we need a 3 out in front. So there is the derivative of sine of 3x using the chain rule. Following that same pattern, we have e to the 11x. It's going to be 11e to the 11x because the derivative of 11x is 11. And it doesn't take much to transition the next one to minus 2e to the 2x. Now from here, this looks pretty safe because I know the cosine of 0 is 1. So plugging directly in at this point, I know that our denominator is going to be 3 cosine of 0, which is definitely going to be equal to 3. In our numerator, we'll have 11e to the 0 minus 2e to the 0, which is 9. And here we have 9 over 3 equals 3. So this one we had to use L'Hopital's rule. We did not have another option. I mean, I guess you could have graphed a bajillion points and guessed, but yeah, that's no calculator, so you'd have to do that by hand. So good luck fitting that into an ESQ. Question C, I want to throw one in there that involves some one-sided limitness. This one doesn't exactly have it. It's not exactly explicitly about one-sided limits, but you need some understanding of them to answer it. We're supposed to evaluate the limit as x goes to 4 of p of x if p of x is this piecewise function. So effectively, if I'm going to do this formally, and I know in an ESQ, like formalism gets set aside just a little bit, I want to verify if the limit exists by using what we called the double one-sided limit theorem last night, but that's name's not technically like some sort of formal name. It's just a nickname that I gave it. So what we're going to do is we're going to check the left-hand and right-hand limits and see if they match up. If those limits match up, the limit exists. If those limits do not match up, then we have a jump and our limit does not exist. So that's what the stakes are high in this case. Whew. Okay, so the first one, if we're going to evaluate the limit from the left side, those are the smaller values. So our left-hand limit will come from there. This will be 3 to the 4th minus 1. That's 81 minus 1 equals 80. Down below, we're going to have 5 times 4 squared. And by the way, that's 5 times 16 is 80, so we're actually in the ballpark. There's some interesting stuff happening here. Excuse me. But this time we add 2, which gives us 82. Now, last time I checked, the 80 and 82 are different numbers. So what we've just shown is that the limit as x goes to 4 from the left side of p of x does not equal the limit as x goes to 4 from the right of p of x. And what that tells us is, therefore, that the limit does not exist. In fact, we have what's known as a jump at x equals 4 because the left-hand and right-hand limits do not exist. As far as our answer, though, writing DNE, preferably in all capital letters, maybe even with periods in between, would be perfect. New AMD software, Adrenaline Edition. No. There's question 3C. Okay, question 4 involves limits at infinity. This is a topic that wasn't on the original creation of this document. It was on the last ones that I've been giving the previous few years, but this wasn't on the original, but it's a really essential topic for the second half of Calculus BC when we deal with some of the sequence and series convergence problems. So I think it's one that just sort of has to have a place in here. And these problems tend to be quick if you know a few techniques. So in this case, we're asked to limit as it goes to infinity of this ratio of two polynomials. What I'm going to do first is I'm going to go ahead and just rewrite this in a particular way. As I've said before, we want accuracy more than precision, or we demand or we desire accuracy over precision here. What I mean by that is upstairs, obviously, we have 3n to the 4th plus 3n squared plus 1. Down below, though, we have 5n squared plus 3 squared. And that one's not actually bad to multiply out. You can do it pretty reasonably. In fact, I think it's going to be 25n squared plus 30n plus 9. But we don't have to do it that way. What we really need here with limits at infinity is we need to consider the highest degree terms. So in fact, writing this out like so is actually all we really need. At this point, we can see that the highest degree term in both the numerator and denominator is degree 4, which means this limit is going to be equal to the limit as n goes to infinity of 3n to the 4th over 25n to the 4th. Those n to the 4ths go away, and we find that this limit is equal to 3 over 25. Now, if it bothers you that that is the answer and that I got that answer without doing something super rigorous, well, I mean, that's sort of your fault now that I'm doing a bunch of extra work, and probably the rest of your class is mad at you. Well, I guess no one's watching this, so they probably aren't. This is probably a safe time to do it. But the one thing that you can do here is you can also use what we called nerfing last year. Basically, we can do some controlling term analysis. And the way that that works is you can take your numerator and denominator, and I will admit it does help to have it multiplied out, and you can multiply by 1 over n to the largest power on any term of the rational expression. So in this case, that's n to the 4th, so 1 over n to the 4th multiplied all the way through will give us a new version. As a heads up, if you actually evaluate this, and you probably will if you're sticking around watching this part of the video, when you distribute it through, it creates very different looking terms. We get 3, because the n to the 4ths divide out, plus 3 over n squared, plus 1 over n to the 4th. And likewise down below, you get 25, plus stuff, and then plus 9 over n to the 4th. And the important thing for us to recognize here is that as n goes to infinity, this becomes 3 plus number over infinity, which is 0, plus number over infinity, which is 0. And then down below, we get the exact same setup. All those other terms go to 0, and we get 3 over 25. This is the formal way to do it. Like, this is the formal way to, like, algebraically show it. It's basically a trim the quills technique, for those of you that remembered that from last year. But, you know, there's lots of ways to get through here quickly. I think a lot of people just look at this and go 3n to the 4th over 25, n to the 4th is 3 over 25. That's great. That's fine. Like, you wouldn't be judged in all likelihood on your work for a problem like this. You'd be judged on your answer's correctness. Question B, makes it look a little bit simpler even maybe than the previous one. Like if you were expecting everything to escalate in difficulty, well, surprise, here's what we got. But the one thing that I will note here is that the difficulty lies in the degrees being different. So in all likelihood, what I would hope you could see is that this would simplify and clean up really quickly. But instead, let's actually do that nerfing strategy. Well, here, let me do this. As I said, if you do this for real, this is equal to 0. Now, if you're wondering, like, why? Why is it equal to 0? Oh, why, oh, why? I was going to say, oh, where has my little dog gone? But that's a song or something. What I'm going to do is I'm going to take this and I'm going to perform that nerfing technique by multiplying up and down by 1 over the largest power of n. So the largest power of n is n to the 4th, so 1 over n to the 4th, 1 over n to the 4th, and then I'm going to distribute this in all sections. Now again, this is extra work. If you're like, why am I showing that? Why is he showing this when I already got the answer? Yeah, I know. If you already got the answer, then stop. Like, it's an ESQ. Like, keep moving forward. But if you're confused by why it's 0 or what I did to get 0, this is the path to get there. Our limit in this case becomes stuff over 7 plus 8 over n cubed. And then in our numerator, really, really subtle thing that you might actually miss when you're doing it, becomes 13 over n. Now when you plug in infinity here, you get 13 over infinity, all divided by 7 plus 8 over infinity. I mean, he wants to say infinity cubed, cool, be my guest. But the thing is, any number divided by infinity is going to approach 0. So in the limit, this is equal to 0 over 7 plus 0. And 0 over 7 is 0. So there's our limit. Exactly what we said it was a few minutes ago. So there it is, more formally done. And then it looks like, yep, there it is. So it looks like the final question that we'll take a look at here is in the limit section, the limit at infinity section, excuse me, is the limit as n goes to infinity of e to the negative n minus 5 all over 4 e to the negative n plus 7. And this is one where I think the temptation is just to immediately do some sort of L'Hopital's rule. It's not. This is a direct substitution problem. It just doesn't look that way. So here's what I mean. If we evaluate this, actually, let's do direct substitution. What am I doing? This is going to be e to the negative infinity minus 5 divided by 4e to the negative infinity plus 7. Now, to evaluate this, what I'm going to do is I'm going to point out that e to the negative infinity is 1 over e to the infinity. And that is the same thing as 1 over infinity, which is 0. Therefore, if I bring this up, this limit is equal to 0 minus 5 over times 0 plus 7, which means this limit is equal to negative 5 over 7. It's so easy to just assume that this is going to 1/4, but you have to read these things carefully. And I feel like this is a perfect kind of example for that, because this isn't a difficult problem on its own, but if you're careless while reading the limit and reading and extracting information from that limit, then you miss the question. And I think that feels just in the mathematical sense. Obviously, in a perfect world, none of you would miss anything ever. So I get it. Okay, you know what? This will be the last one. I don't have any gas left. I'm literally running out of gas. Let me drink some water one more time. I did one of these videos for AB last quarter, and I actually fell asleep in the middle of it. Like while standing up, talking. It's very weird to look at, so I deleted it. But, I don't want to do that. It's embarrassing. So, and actually, I don't know. Am I using too much of my CPU? No, only 2.5%. Okay. So question 5 is all about writing the tangent line. And like I said, I wanted to give you a good spectrum of the sort of questions I might ask. I will say if 5A appeared on an ESQ, that was me trying to give you the gift of an easy question. This is too basic to ask on a BC ESQ, but we're here, so let's do it. Like when in Rome. So first of all, to get the y1 value, because remember our goal here is to write our tangent line equation as y minus y1 equals m times x minus x1. Based on that, to find y1, I'm just going to plug in 1. So that'll be 3 times 1 squared plus 5, which is very clearly equal to 8. To get our slope, I'm going to take the derivative first, which is going to be 6x plus 0. And then I'm going to evaluate it at x equals 1. That means that our slope is going to be 6 times 1 equals 6. Based on all of that, we have y minus 8 equals 6 times x minus 1. So like I said, this is too clean. This is a day 1 derivatives tangent line. Like just too simple for what we have. Question 5b, yeah, you got to know some rules here. This is technically a chain rule problem. It requires your knowledge of exponential differentiation. However you want to do it, I guess I could demonstrate the full chain rule in this case. Do I want to? I'm not going to do the full chain rule. Instead, I'll point out that the derivative here is going to be equal to e to the stuff times the derivative of the inside, which is the derivative of 6x plus 1. If we clean this up a little bit, that's 6x plus 1 being a line. Its derivative is its slope, so that'll give us a scalar of 6. We'll have 6e to the 6x plus 1. Now here, though, they wanted the derivative at x equals negative 1, or sorry, the tangent line at x equals negative 1. So first of all, we can plug in x equals negative 1. Like you might notice, by the way, that I'm doing this out of order from the previous one. I apologize. This will be 6 times negative 1, which will be negative 6 plus 1. So in other words, our slope is going to be 6e to the negative 5, or if you prefer, 6 over e to the 5th. I kind of prefer that one myself. I'm not a huge negative exponents dude. And then lastly, we need y sub 1, which is going to be g of negative 1 here, which pretty clearly is going to be e to the negative 5 for similar reasons, which means we could also write g of negative 1 as 1 over e to the 5th. Given all of that, our tangent line in question is going to be y minus 1 over e to the 5th equals 6 over e to the 5th times x minus a negative 1. So there is our second tangent line. Again, feels pretty reasonable. It did involve chain rule, which can challenge some people, but otherwise a pretty good approximation of what I'm looking for. And absolutely the last question, I am totally running on fumes here. The final one, this is more of an abstract version. I try to put on at least one like this on every single exam. This one also involves the chain rule, by the way, sort of interesting. So we want to figure out the tangent line at x equals 4, given this information. So let's go one piece at a time. First and foremost, y sub 1 is going to be f of 2 times 4, which is going to be f of 8, which, hey, look at that, they gave us that at 7. So if you're scoring at home, which, I mean, I guess you probably are, based on you watching this video, we'll get y minus 7 on the left. On the right, we can already put in x minus 4, since we're doing the tangent line at 4, but we do need to take the derivative of f of 2x. And as I sort of let slip earlier, this one involves the chain rule. It's not a difficult chain rule, but it is a chain rule. So in our case, we're going to get f prime of 2x, and then we'll multiply by the derivative of the inside, which is 2. From there, we'll evaluate it at x equals 4. When we do, we get 2f prime of 8. According to this graph, or this information, it's not a graph really, it's just told to us, f prime of 8 is negative 2, so 2 times negative 2 equals negative 4. So our slope of the tangent line at the indicated point, or at the indicated information, is y minus 7 equals negative 4 times x minus 4. And with that said, I'm going to stop there because I have no gas left. So I'm going to go ahead and render this, I'm going to convert this, then I'll render it, and I'll probably just post this as like the first 5 questions, first 5 questions. So yeah, thanks for watching. Have a good night.